Hello, class. We're going to start chapter 4 now. This is section 4.1, minimum and maximum values. If you recall, back in chapter 3, we learned how to take derivatives, many various ways to take derivatives. We have the power rule, quotient rule, the chain rule, product rule, logarithmic differentiation, a whole bunch of rules. Now, in this chapter, we're going to focus on what do the derivatives tell us about the function, where are they useful, okay? The first thing we're going to study is minimum and maximum values. Now, when we're going through this, I hope you would have my lecture notes printed out or at least open in front of you on your screen while you're watching this video. Due to limited board space, I'm not going to write the definitions on my board. I'm going to use it to draw my pictures and do examples because you have the definitions in my lecture notes. Okay, so the first definition says let C be a number in the domain D of a function f. Okay, so f is some function. It can be whatever function we want, and it has some domain D. For example, if our function was a polynomial, the domain would be from negative infinity to positive infinity, all real numbers. If our domain was a rational function, the domain would be from negative infinity to positive infinity, except the numbers, if there are any, that make the denominator equal to 0. Okay? So, let C be just some number in that domain. Then f of C is the, now here's the first definition, f of C is the absolute maximum. Now, in some books, you may see the term global maximum. In this book, they stick with absolute maximum. So, f of C is the absolute maximum value of f on D, on the domain, if f of C is greater than f of x for all x in D. Okay, so there's the definition. Let's go ahead and draw a picture and illustrate what this looks like, okay? So we're going to look at our most basic function that has a maximum and x squared, or negative x squared plus 1, okay? Negative x squared plus 1 looks something like this. There's 1. And it goes something like that, okay? Now, as you can see, we do have a maximum right there, but now let's look at this in terms of the definition. Okay, so it says, let C be some number in the domain. This is a polynomial, so the domain is from negative infinity to positive infinity. So we need to, there is some number in that domain such that f of C is bigger than or equal to f of x for all x in your domain. If we could find a number C that satisfies this inequality right here, we would say f of C is the absolute maximum of our function f. The absolute maximum occurs at C. The maximum value is f of C. Okay? So, now let's go ahead and take a look at this. Let's see. In red, I'll mark our maximum. It's right there. There's our maximum value. There's f of C. Incidentally, on this graph, this right here is f of 0 because we got a concrete function right there. That is f of 0, which happens to equal 1. Now, if you were to look, I'm going to do this in black. If you were to take any x value in the domain, so if I take an x value anywhere in this interval right there, you see it's going to be mapped to these points right there. Okay? Now, if you look, if I go over to the y-axis, all of these numbers, all these f of x's, are always less than our f of c right here. So this is our f of c. C is just equal to 0 in this case. Okay? So for every x value, even if I go way out here, if I look out here, I'm going to go down here, it's going to hit the function somewhere down there. That's obviously way below that maximum right there. So what this definition is saying, it's the absolute maximum, meaning there is no other number in the on this function that is larger than this maximum. It is the absolute maximum. That's another reason why they call it a global maximum. Global meaning everywhere on the domain, which would be, in this case, you could think of as the entire globe, it is the highest value. It's the global maximum. Okay? Now, we have a very analogous definition for an absolute minimum, okay? It says, let's see, I'm going to read the whole thing again. Let C be a number in the domain D of a function f, then f of C is an absolute minimum or global minimum value of f on the domain D if f of C is less than or equal to f of x, for all x in the domain D, okay? So, let's look at f of x equals x squared plus 1. Alright? So, again, it's a polynomial. The domain is negative infinity to positive infinity. If I were to look at the graph of that, that's 1, and it goes something like that. Okay? So, again, let's go ahead and mark our minimum in red. I guess I should have used blue to draw that, because the red blends in with the black. Well, in any case, if you see any number I pick in the domain, just any x value, if I go up to the graph and go over to the y-axis, this would be my f of x. This right here is my f of c. Again, in this case, just because we have a concrete function, c is equal to 0, so it's really f of 0, which is also equal to 1. But in any case, any x value that I pick anywhere in the domain, it could be really close, it could be really far away. If I were to go over to the y-axis, I always have this inequality. F of c is less than or equal to f of x for all x. So, just to reiterate, this f of c is an absolute minimum because everywhere on the domain, f of c is always smaller or equal to than any f of x. Again, this is for all x. No value on this parabola, no value on this function is going to be smaller than this minimum value here. So it is the absolute minimum. Okay? Now, we have another little note that I want to talk about. Now, the absolute minimums and maximum values, again, this note is on my lecture notes. The absolute maximum and minimum values of f are called the extreme values of f. Extreme meaning that is the highest value you can get to, the lowest value you can get to. Those are the extremes of your range. You can't go any further beyond that. So it's just another name for them, okay? And it's the actual value of the minimum or maximum, not the x value where it occurs at, but the y value. And I'll point that out when we do examples. Alright, so we got two more definitions. Now, these two definitions are going to seem very analogous to the previous two definitions. It says the number f of c is a local maximum value of f if f of c is bigger than, greater than, or equal to f of x when x is near c. Okay, so there's a difference between absolute min and max and local min and max. So let me go ahead and draw you a picture. Okay, so this is just some generic graph. I don't know what this looks like. I don't have like an actual function for it. It doesn't matter, okay? Now what we're gonna do is we're gonna look locally. If you look at the previous term for the definition, there was global max, global min, global meaning everywhere. Local means just in a small little area, okay? So if you look right here, right there, and if we were to just have, like, say that's our x-axis, say that's our y-axis right there. Right here, whatever this c value is, if I look near that c value, and when we say near that c value, we mean close to it, not very far away, because if I go too far away, you've got a maximum here, you've got a maximum here. So when we say near, we mean very close to it. Okay? So if I choose any x value that is near c, and I were to go up, you're going to see that anywhere I choose near it, this f of c is always bigger than or equal to f of x. So we call this a local maximum. As you can see, it's a hill. So when you're near the hill, the highest point should be the maximum, okay? Now, if we were talking about absolute maximum, we would look for the highest point on this graph, and that would be the absolute maximum. Okay, we'll go through a process on how to do that. There's like a step-by-step process what you can do to find the absolute min and max towards the end of this section. Okay, we could use this same idea and explain a local minimum. So if I look over here, right there, this is my new C. I'll call it C star so you don't get it confused with this C right there. Now, this Y value here is f of C star. And again, if I were to choose any x values near C, so x values here, x values over here, anywhere I go up to the function, and if I were to like draw an imaginary like y-axis mimicking the scale over here so we don't have to go all the way over there, every function value we always have this inequality. F of c is less than or equal to f of x. Sorry, f of c star. So it says the number f of c is a local minimum value of f if f of c is less than or equal to f of x when x is near c. We're near c, this inequality always holds when we're near this c star, therefore this is a local minimum. Okay? So now just another little note. When we're finding local mins and local maxes, local mins and local maxes, and absolute mins and absolute maxes. So there is only one absolute min slash max. That's if they exist, okay? There's some functions that don't have absolute maximums. There are functions that don't have absolute minimums. But if they do have an absolute minimum or maximum, there's only one of them. So a function can have more than one local min slash max. Here's a key difference between the two definitions. For a function, if it has a local min or max, there's only one I said local min. I meant to say absolute. If there is an absolute min or max, then there's only one of each, okay? If there is one of each, okay? Now, a function, however, can have more than one local mins or maxes, okay? You can have more than one of these, but you can only have one of these, of each one, okay? Now let's go ahead and look at an example. First example I'm going to look at is a graph. It's the graph of y is equal to 3x to the fourth minus 16x cubed plus 18x squared. And then I'm going to look at it in the interval -1 to 4. The graph of this is also in your book. I forgot to write the page number down on here. But it is in your book if you look at 4.1. But I'll draw the graph for you. If you'd like, you could also get out your calculator and type this in and change your window. Let's see, the window that I'm using, these are the x values. So this would be your x min, this would be your x max. The y values, I can tell you exactly what I have. I've got it going from -35 to 40. So change your y min to this, change your y max to that. And then you can look at the graph really nicely on your calculator. Now, of course, my drawing up here is not going to be as good as the calculator. See, that's x equals 0. Let's see, 1, 2, 3, 4, -1. This point way up here is -1, 37. Let's see, this point down here is 0, 0. 4, comma. Okay, so the graph looks something like this. Goes down like this, hit 0, crosses through here, goes something like that. Alright, so this is roughly what the graph looks like. Now, we're going to find where the local mins, local maxes are. We're also going to find the absolute minimums and absolute maximums. Now, you're going to wait. I'm going to show you something in the next example. There's a reason why we put a point here. We stopped here. This is where our graph is starting, okay? This is where our graph is ending. A normal polynomial like that, it actually keeps going and keeps going. We're not going to keep going. There's a reason for that. We'll come to it later. I'll explain to it later. It's when we're talking about the extreme value theorem. Okay, but let's go ahead and find our local mins and our local maxes. So if I look right here, that point right there, this is a local maximum because you've got a hill. So anywhere near wherever the C value is, on my picture it looks like it's at 1. It could be at 1. I have no idea. I didn't compute the numbers where they are. Our job here is just to find the local mins and local maxes. So right here, wherever it is, that's our local max And then we'd go over here to look at the y value, and then the value of this number right here would be the local maximum value. Now, if we look here at x equals 0, again, we have like a valley. Anywhere near a valley, there's going to be a lowest point right here. This right here is a local min. Now, if we go over here, we look at it, it is also a local min, because anywhere near, like if I go up here, anywhere near this value, again, I'm at a valley. So, at the very bottom of the valley, everything is above me, so I'm at a minimum. Now, there are no more like valleys or hills, so we've got all of our local minimums and all of our local maximums. But now let's go ahead and find the absolute minimum and the absolute maximum, okay? So, looking at this function, what is the highest y value that you see? Give you a second, think about it. The highest y value, yes, this is a maximum right here, but when we're talking about the absolute maximum, we're talking about the highest value of the entire function, starting from the first number in its domain all the way to the last number in its domain. And it happens to be this value right here. It has a value of 37, okay? So here, ABS for absolute, this is the absolute maximum of the graph. Now, if we look, we want to find the absolute minimum. We need to find the lowest point in the graph. Yes, we have a minimum right here because it's a valley. We have a minimum here because it's a valley, but this one right here, it is the lowest point. If I were to go over here to the y-axis and find its actual value, its lowest point is down here. No other point on this graph is lower than this point here. This local min happens to also be the absolute minimum. And that's okay. Some local mins and maxes could be the absolute min or absolute maximum value. Okay, that is very possible. Okay, so now for the last example in this video, we look at a very simple function, which is just x squared. So if I were to draw the graph of x squared, it's right there. We can see, and we're talking about on its entire domain, we're not closing it off like the last example. You can see that right here, no other point is smaller than this value right here. This is the local minimum of the graph. This is also the absolute minimum of the graph. Now, since we're considering this function on its entire domain, this function keeps growing and growing as we go in both directions. So, there is no absolute maximum. There is no local maximum. We can't find any. Now, if I remember correctly, I have seen in some books will say the global maximum is infinity because it does go off to infinity. For our purposes, we're just going to say it does not have a global maximum. And analogous, if I were to put a negative in front of here, it would be flipped, and it would have local max, absolute max, but it would have no local minimum, okay? So that's just like a special example. You don't always have to have absolute mins or absolute maxes. Now we're going to look at another one. X cubed. Let's look at the graph of x cubed. So something like that. Nowhere on this graph do you have any valleys or any hills. You would not be able to find a piece of this graph that satisfies any of the inequalities like that. Okay? If you look, this graph is forever increasing. It keeps getting bigger and bigger and bigger. So, therefore, you can't have any local mins or local maxes, or any absolute mins or absolute maxes. And again, we're considering this on its entire domain. So this graph keeps going down here, this graph keeps going up there.